so our goal for today's lesson is to graph logarithmic functions. That is ultimately what we are going to go ahead and take care of. And I just need to kind of review with you something really quickly before I jump on in to graphing full-out logarithmic functions. I wanted to take a second to talk about exponential functions. So think back to maybe your Chapter 7, 1 to 7.3 test, or maybe think back to your review assignment, but I want you to tell me about what you recall from your experience in graphing exponential functions. What are just some things you remember about going through that process? That'll be a nice way to start off today. Anything that appeared on your graph? Good, Bree. Yes, we always look for critical points. That is true. So mainly we look for intercepts. That is true. Your logarithmic functions might have an intercept as well. So we'll have to think about that today. That's true. Let's go off what Bree said maybe a little bit. When you were graphing exponential functions, for instance, if they didn't have an h or a k, so just your parent exponential functions, we had two types. What were they? Two types, depended on your b value. Good. Decay and growth depended on the b value, right? So do you remember which one was which, Heather? No, it wasn't negative or positive. Well, perfect. So if your b value was bigger than 1, it grew. If it was between 0 and 1, it decayed. You can have logarithmic growth and logarithmic decay as well. Guess what it depends on? The value of b. So we're going to talk about that today. What else were some characteristics? Maybe Danielle, what do you think? Do you remember anything about exponential graphs? What are some characteristics, things you had to show on the test? What kind of asymptote? It was a horizontal asymptote. If we take into account this idea that exponential and logarithmic functions, yeah, you're going to need to get rid of your hat, Calvin. If you take into account exponential and logarithmic functions are inverses of each other, then true story, we had a horizontal asymptote on our exponential functions. These graphs up here, they're going to have vertical asymptotes today. Okay. You also had to tell me a little something else. It was related to the asymptote. After you were all done graphing, you filled in 2 blanks at the bottom. Yeah, the domain and the range. Very good. Do you remember anything about the domain for exponential functions? Good, Will? It was all real numbers. Yeah, negative infinity to positive infinity. What about the range? It was usually affected by what Danielle had to say. The range was related to what for an exponential function? Yeah, Izzy, what were you going to say? Yeah, the asymptote. The asymptote sort of gave you a little insight into the range for your function. Okay. So, for today's lesson, we have to talk about logarithmic functions. All this stuff you just talked to me about as far as exponential functions were concerned also apply to logarithms because they're inverses of each other, which means we swap out the x and the y. The first thing you're going to notice in this particular chunk of notes is that if b is bigger than 1, you're going to have a growing logarithmic function. And if it's between 0 and 1, you're going to have a decaying logarithmic function. Follows the same rules as exponents, exponential functions. So that is true. In general, when we go to graph y equals log base b of x, we actually end up using an exponential form of that equation. And that's, again, because exponential equations and logarithms are actually inverses of each other. So in general, when we go to graph a logarithm, what this is saying is that because these two functions are inverses of each other, we could just take our exponential function and flip it over the line y equals x. Now, you'll recall that we never did that when we did our little blip in the radar in Chapter 5 on inverses. We never did that. I never made you manually flip a graph over the line y equals x. This is a tough question. I'm real curious. We never really flipped it over the line y equals x, but we did graph inverses. Do you remember the real quick way we did it? Do you remember? Oh, no, that was like translating. This is a hard question because we just did it like one day. When you graph an inverse function, it has to do with the t-chart. You graph the original function and you make a t-chart. And then to get the inverse, do you remember? Well, yeah, you just switch out the x and the y. So if you go to graph an exponential growth function and then just change out the x and the y on your t-chart, you get a logarithmic growth function. So for instance, right here, I see an exponential function that grows. This tells me that this b value for whatever this thing is a number that's bigger than 1. This would be our sort of original graph. You could draw it in as a dashed graph. So that's your exponential function right there. If you flip it over the line y equals x, so that's the line y equals x right there, you actually get your solid logarithmic function. Because logarithms and exponents are inverses. So this would be y equals log base b of x. And then this function right here was our exponential, y equals b to the x. Now, you folks said it originally. I think it was Victoria. You said it. We have two types of graphs. You have exponential growth and you have exponential decay. Maybe it was Heather. I want to make sure I'm giving credit where credit was due. It might be exponential growth or it might be exponential decay. So we have growth for logarithms and we also have decay. So here what I see on this side, I see my exponential decay function. So this is our decay. This guy over here was our growth. You have your exponential decay function. This results out of your b value being a number in between 0 and 1. It could be like a fraction or a decimal. So that's your exponential function. If you flip that graph over the line y equals x, you would get a logarithmic decay function. Uh-oh. So I just wanted to point one more thing out to you, how in fact these things are actually inverses of each other. Back to what Will was saying, you could swap out your t-chart, change out your x and your y. If you look at, for instance, our exponential growth function over here, there's a point on there. Do you see it? Right there. That's the point 0, 1. So if I look at that point, that was my y-intercept. It actually, when I flip it over the line y equals x to graph the inverse, it's not 0, 1, it's 1, 0. So the y-intercept on the exponential function actually becomes the x-intercept, which is what Bree was talking about for our logarithmic function. We always look for those intercepts. They're important points. So that's kind of interesting. Happens on decay too. If I look at my exponential function here, I have the point 0, 1. If you interchange the x and the y value, you do get the point 1, 0. It turns into the x-intercept on our logarithmic function. What you're going to notice in general, when we talked about our exponential functions, you folks just kind of said this to me. Our exponential function had, if you'll recall, I'll highlight it so we don't get confused. We had horizontal asymptotes. Do you remember that? Our exponential functions got really, really close to the x-axis but never touched it because you can't really get negative values or 0 back out. That happened. So we had horizontal asymptotes for exponential functions. What you're going to see for logarithmic functions, if we're sticking with the idea of switching out x and y, our horizontal asymptotes were lines, the x-axis, that's an equation of the form y equals 0. But like I said, if we're sticking with this idea where we swap out our x and our y values, we don't end up with horizontal asymptotes for our logarithmic functions, do we? You could kind of see them on there. You get really, really close this time around to the y-axis, but you don't actually touch it. We said at the very beginning of this section on logs, you can't take the log of a negative number, and that's kind of why. You're never going to see your logarithms unless you translate them over here in negative land. So we get really, really close to the line x equals 0, but we don't actually touch it. This ultimately affects our domain and our range. We could swap out our domain and a range for our exponentials. You might recall that the domain for an exponential function was all real numbers. I think Will said that one, right? So that's going to actually be our range for our logarithms. And you might also recall that for your exponential functions, your domain was restricted, right? I'm sorry, I said that backwards. Your range is going to be all real numbers, but the domain is going to be restricted for your logarithmic function. It's going to be restricted based on your horizontal asymptote here, so we don't get to 0, and then you do head towards positive infinity. You can kind of see it as you were walking along the x-axis right there. You started almost at 0 and kept walking to infinity to get all of your values in. So we're going to do 3 of these today together as a class. That was just a little bit of background information on what the graphs are going to look like and where they come from. If you want to write these steps down, you totally can. There's some space at the bottom of example 7. You'll see there's a big space there in your notes. In general, these are the 4 steps we're going to use for producing graphs of logarithmic functions. So step 1, we're going to write the log in exponential form because it's easier to come up with numbers for a t-chart that way. It's supposed to say step 4. So there are 4 steps. Step 1, you're going to write the log in exponential form. Step 2, you're going to make a little t-chart for yourself. You then connect the dots to make a graph. And then you take that graph and you translate it if you have to. If there's an h and a k value, you have to move it. And then the last step, our logarithmic graphs are going to have vertical asymptotes because our exponential graphs had horizontal ones. So you're going to label your vertical asymptote, draw it in as a dashed line, and then give me the domain and the range for each graph. So those are our steps. So one of the big ideas after you finish copying down those 4 steps, one of the big ideas that I have to teach you in Algebra 2 is to be able to look at an equation and kind of picture what the graph looks like. For this section, it's important to be able to do that a little bit ahead of time. And what you're going to kind of be thinking about is the graph going to grow or is it going to decay? And remember, to make that determination, we look at the b value in this chapter. B values bigger than 1 mean that your graph is going to grow. If your b values are between 0 and 1, it means your graph is going to decay. So after you're done copying your 4 steps, let's just talk about these equations for just a second. Take a look at part A. The base is 2. Is that going to be exponential growth or exponential decay? I meant to say logarithmic because we're doing logs. Is it logarithmic growth or logarithmic decay? What do you think, Will? It is growth. Good. So this b value here, bam, that b value is bigger than 1. So this graph is going to grow. So now we can go ahead and go through our steps. All right, step 1, we write this as an exponent. We're going to use our log cycle to do that. So what we're saying here is that 2 raised to the power of y gives you x. That looks different than the equations that we graphed at the beginning part of the chapter, doesn't it? Because the x and the y are in the wrong spot. But if you think back to the idea that what we're doing is actually the inverse of the exponential equation, that makes perfect sense because you switched your x and your y. So if you swap out the x and the y, you're actually graphing a log. Good. We then use this equation to make our t-chart. You could think of some friendly outputs for this particular function, but those outputs are actually going to be your values of x. So for instance, I know that this number over here, this x value, I'm circling with my finger right now, this x value, it could be 2 if I let y equal 1. So in other words, if I raise 2 to the first power, I would get 2 back out. So I usually pick friendly outputs, x values, kind of first, and then I think about the corresponding y value, however you want to do it though. But I know that, for instance, I wouldn't want to pick a value of 7 for x. You know how you arbitrarily usually pick numbers for x? I wouldn't want to pick a number like 7 for x because, well, 2 raised to what power gives you 7? You know, I can't even do that in my head. I could get an estimate, but I can't actually get that number. I want some easy points. So this goes back to that whole idea of pick an easy set of numbers for yourself. So for instance, I know that I could get 1 back out of this equation if I just raise y to the, make y the 0th power. 2 to the 0th power is 1, so that's a pretty easy point to plot. Also, I think I could get a half out by just using my upstairs downstairs rule a little bit. If I let y equal -1, I'm going to get a half. I could probably get 4 back out really easily because that would just be me squaring 2. So again, I'm just picking some friendly outputs. And look, I have, you know, a little bit of negatives, some zeros represented. Looks like represented. That's not a word. Represented. So I can go ahead and plot these points. That's what I'm going to do. Got my easy t-chart. Let's graph some points. For instance, I'll graph the point 2, 1. So over 2 and up 1. And then 1, 0. That's another point I found and thinking about my t-chart. And then 1/2, -1. And then all of a sudden we go, you know, over 4. 1, 2, 3, 4, and up 2. Could I possibly get any negative x values? Is there anything you could put in for y that would get me a negative x value back out? No. How about 0? Could I get an x value of 0 back out? No, there's nothing you could raise 2 to get 0 back out. So notice therein, when we start to think about these possible values on our t-chart, we can't even touch this line. So bam, there's your asymptote right there. And we can't even touch this line. We can't even cross it. So what we get is this sort of reflected exponential function that gets really, really close to the line x equals 0, but it can't cross it. So that's the graph, but I'm not quite done. There is a 4th step, and I took care of part of it. I labeled my vertical asymptote. So logarithmic functions are going to have vertical asymptotes. And then I have to state the domain and the range for that particular graph. So the domain, possible values of x, for this graph, we get a restriction. And it makes complete sense if you think back to the fact that logarithms are actually inverses of exponentials. Our range was restricted on exponentials, so our domain gets restricted for logarithms. So as I'm walking along the x-axis, I see that I'm only really allowed to have positive x values. Reason being, you also can't take a log of a negative number. So what we get right here is values that get pretty close to 0, but then head out towards positive infinity. And And then our range values, if I were walking along the y-axis, I see values everywhere, all over that y-axis. So that's actually negative infinity to positive infinity. You're going to get your test back a little later on today. And we talked about your review assignments. When you graphed your exponentials, your domain and range were just the reverse of this. All right, think you got the 4 steps? Because I want you to try part B. You're going to go ahead and take care of that for me real quick. Keep in mind, I see a B value there. B is 1/3. This will not be a growth graph. Since B is a number between 0 and 1, I can look at this right now. My graph isn't going to go up. It's going to go down as X increases. So we see decay there. That some of the newer calculators actually have the base where you could change it. So you could do log base 2 of 7 in your calculator, and I don't really care what your calculator can do, honestly. I want you to understand what a logarithm is. So when you go to get your test next week, there's going to be a portion of your test that you can't have your calculator on. But as I walked up and down the rows, I heard buttons, and I saw numbers like 0.56, 0.67. Like, that's not you thinking about the problem. That's your calculator. You know, that's you leaning on your calculator way more than you should. So please understand that I'm saying make an easy T-chart for yourself. In other words, you should understand how a series of inputs can give you outputs for this type of function. So you can see the numbers that I picked up here. For instance, 1, 0 again appeared on this graph, and it will all the time because of our 0 exponent property. If you let your exponent be 0, you're always going to get that 1 value back out. That just happens. Then I was like, oh, I could use my upstairs-downstairs rule to get some whole numbers to plot. For instance, if I make this exponent -1, that's me using my upstairs-downstairs rule. You get 3 back out. In the same regard, if I plug in -2 for an exponent, I get 9 back out. And then I was like, well, I should probably have a couple fraction values there because I know this has an asymptotic behavior. If I just let my y value be 1, 1/3 to the first power, that's going to give you 1/3 for your x value. So this is the T-chart that I graphed. Notice I don't get any negative x values ever, because there's nothing I could make a y value for my exponent that would give me a negative x back out. So what I see is a graph that really just doesn't ever creep into quadrants 2 or 3, ever, because those have negative x values. However, my range is defined everywhere. I go from negative infinity to positive infinity. So after you get your vertical asymptote and write your domain and your range, you're done. That's it. Okay, questions about that? No? Okay, so for the next problem, you'll see visually speaking it's a little bit different because we have an h and a k value thrown in. But the first thing we're going to do, well, the first thing you're going to do is graph the logarithmic function as the parent function for this graph. So we're going to spend a little bit of time first graphing y equals log base 3 of x equals y. And what I notice is since this base is 3, I'm going to get a growing logarithmic function. And then I usually think about this using my log cycle. The function I'm thinking about to make my T-chart is 3 raised to the power of y gives us x. And again, you know, I always think to myself like, oh, I have that 0 exponent rule where I could just get 1 back out. So that 0.10 is always going to be a part of that graph. And then I think to myself, well, what are some easy outputs for x? Like 3 is. If I make the exponent 1, I get 3 back out. If I make y -1, I'd get 1/3. That's not too bad. If I make y 2, I'd get 9, because 3 squared is 9. If I made y 3, I'd get 27, but that's not going to fit. So that one, not so much. You'll notice that I'm never, ever, ever going to get any values that are negative in the column for x, and I'm never going to get 0 as a possible value for x. So now I got to plot these. For instance, I got to plot the point 1, 0. Watch, because they scaled this x-axis by 2s. So over 1, 0 is actually right there. And then over 3, up 1, looks like that. Over a third, down -1 is right there. Over 9, up 2, 2, 4, 6, 8, 9, up 2. It's right there. And 27.3 doesn't fit. So you see we do get that logarithmic growth function for us. This graph goes in as dashed. This is just the parent function I'm drawing in right now. Okay, then I look at my original function that they gave me in the problem here. And I'm like, oh, look, there's a -1 in there. That means this graph and my vertical asymptote, the first one, the entire graph along with the asymptote has to move to the right 1 space. And then the whole graph is also going to move up 2 spaces based on my k value. So I'll take all my points, move them to the right 1 space, not 1 full tick mark because this graph was scaled by 2 on the x-axis, so just be cautious of that. For instance, if I move the point 1, 0 to the right 1 and up 2, it moves to the point 2, 1. I'm sorry. It's right 1, up 2. So yeah, 2, 2. And then if I move 3, 1 to the right 1 and up 2, I'm going to move it to the right 1 and up 2. This goes up there. 1/3 -1 to the right 1 and up 2 goes here. Move 9, 2 over. So 9, move it over 1 and up 2 goes there. And then 27.3 does. So now we get this. The whole graph moved over, including the asymptote. I have my new asymptote at 1 there. And there's my new graph of my translated logarithm. You'll notice that the domain has changed. You can't take the log of a negative number. We talked about that when we first did our definition of a logarithm. Can't take the log of a negative number, which means that our x values can't get to 1 really. So our domain goes from 1 to positive infinity. And then the range is defined everywhere. Other questions about how to graph? All right, so we had 3 of those today. Now what I want you to do is get a little practice in.